Okay, so far we have seen how to implement the batch gradient descent, right? And now let's focus on the stochastic gradient descent. Now, before we jump onto the stochastic gradient descent Python code, let's see what it has changed from the batch gradient descent. So in the batch gradient descent, we took the entire data set and we have processed it 2000 times, right? Whereas in stochastic gradient descent, if this is my entire data set, what I'm going to do is I'm going to randomly take one record, okay, calculate all the model parameters, okay, update my model parameters, and then I will randomly choose another training sample and keep repeating it. Now, what is the benefit for that? So the benefit is, instead of taking the entire data set or in all the iterations, it will be quite fast, right? Because we are taking only one sample at a time. And that is why this can be also used in out of core learning process as well, because it can be then passed on outside your device for processing. Now that is one benefit, it will be quite fast. The second benefit of using stochastic gradient descent is we are going to use a dynamic learning rate instead of a fixed one, which was the case in the batch gradient descent. Also, in real life, our error function will not always look like this. So it might look like this also. Now this is my global minimum and this is my local minimum. So what happens is, when we have stochastic or random samples chosen, so my algorithm is dynamic enough to come out of this local minimum and have a more chance to come to this global minimum. If we had taken the entire batch of data, chances are my code could have been stuck here, but my main objective is to reach at the global minimum. So that is the second benefit of the stochastic gradient descent. Because it is taking random samples, so I have higher chance that it will come to the global minimum. But there are a couple of problems as well in case of stochastic gradient descent. One problem is, when we are taking random samples, there is a possibility that I might end up picking the same instance over and over again, and I might totally not pick some samples at all. So that is one challenge, one issue. And the second issue is that once I am close to the global minimum, in case of batch gradient descent, I was definite that I will reach at the very bottom, okay. But in case of stochastic gradient descent, what happens is it comes close enough, so the solution is good but not the optimum, so it will be just close enough somewhere. But what we can see is, or what we have found out is that the close enough is still better instead of getting to the exact the bottom point. All right, so two corrections. One is my learning rate will not be fixed, it will be a dynamic way we are going to calculate the learning rate. And the second thing is, we are not going to take the entire data set in every iteration, rather we'll take one random sample in every iteration. Also, instead of running my code for 2000 times, here we are just going to run it for 50 times, and still we can see that it will get to the close enough value. Okay, so let's look into the code now. Okay, so you can see here I have given a very fancy name called epochs. So epochs is nothing but again the iteration. So how many times you want to run your code using those random samples, right? And it is equivalent to actually number of iterations. But in stochastic gradient descent, because we are not using the entire data set, so that's why it's not called as iterations, rather it's called epochs. So in each epoch, I'm going to take one sample, process all over I have to do, update my coefficients, and then take my next epoch and so on. So basically it's the same thing as iterations. Also, because I'm not keeping my learning rate fixed, rather what I'm trying to do is I'm trying to gradually reduce it. Okay, so you can come up with any function which will reduce the learning rate or a value. Here I'm just taking a some constant divided by some value so that my learning rate keeps reducing. So you remember the problem that we had in batch gradient descent, that if we start with a large learning rate, what will happen is it will just bounce off. So instead of that, what we want to do is we want to gradually reduce our learning rate so that we can reach the global minimum. Okay, remaining portion all remains the same. The only change is that instead of taking the entire batch of data or at the entire training data set, we are going to pick a random sample, and that is why you can see this line random underscore index is equal to a random value. So basically out of 100 I'm just taking a random integer so that I can pick that record and the corresponding output label. And that is why instead of the data matrix X, here you can see I'm just taking a sample Xi. That is the only change remaining. Next is your learning rate. Again, learning rate, instead of being 0.1 as in the case of batch gradient descent, I'm just calling the function schedule so that in every run okay, excuse me. So you can see that my learning rate is just a function of a reducing function. Basically, if I start with a big number, I'm just gradually reducing the value, and with that learning rate and the gradient, I'm calculating my new coefficients. And if you see, my coefficient values are very close to what we got with our normal equation or with our batch gradient descent. So it was 4.45 something, so it is 4.34, and instead of 3.020 something, we are like 3.06 around something. Pretty close, and this method is quite faster compared to your batch gradient descent. Now trust me, you don't have to come up with this schedule and this detailed implementation. Luckily in sklearn we have this already set up there, and it's called the Sgd Regressor. So it's basically a linear regression model using stochastic gradient descent, and you can see all that we have done so far can be done just in 2 lines. So first you instantiate a Sgd regressor, and if you see here, the number of iterations we want to do is 50, which is the number of times it is going to process or update your model parameters. We are not using any penalty. That means we are not going to utilize any regularization technique, and which we will cover in our subsequent projects. And the learning rate by default in case of Sgd regressor is 0.1, but you can start at your own judgment and experience. You can change that value as well. And the next step is just a fit method, and fit method, as we know, just calculates the model parameters. So if you can see here, there are 2 methods, dot intercept underscore and dot coef underscore. They are basically the coefficients that we need for our purpose. And if you see here, these values are again very close to what we have seen so far in our using all the techniques. All right, if you are trying to follow along and write this code, your answers probably will be slightly different because of the random function that we are using. So don't get worried if my values and your values don't change, because we have used some random generator for our input data. So your code and my code will look the same, but the values could be different because of the random function. So I hope you have learned something new and interesting today, and this helps you in preparing the interview question in terms of Python programming. So typically in a Python programming interview, they will ask you in detail and how to implement it. So you might have to end up writing some code as well during the interview. So this should give you a good practice. So thanks for watching, and please make sure to subscribe and press that bell icon to get the notification. We'll come up with more questions and more projects so that it gives you a very well-rounded preparation for your upcoming interviews. Thanks.